Alright, this is the second video for this topic, and I'm going to be referring specifically to Atwood machines. You saw some Atwood machine problems last year, but I don't know if I used this name for them. An Atwood machine basically is a pulley with blocks hanging on it. And they're used frequently in physics classes as like an educational tool. They don't have a lot of practical applications, as you might guess. Most of the time when you see an Atwood machine, it's just going to look something like this. So like a wheel and strings with two blocks hanging on it. There are various modifications you can make to this, like obviously I could put more than one block on one end of the string. One of the most common variants sets one of the blocks on a table, and then the pulley hangs over the table, so something like that. That's called a modified Atwood machine. And you could do other weird things, like if that's the pulley, I could have one block hanging vertically and the other one on a ramp, so you have to do like ramp forces at the same time that you're doing the Atwood stuff. And there's other tricks that can be thrown in as well, like once we've covered friction this year, we can do a modified Atwood that has friction as well as the gravitational forces. And eventually when we talk about rotating objects and like rotational inertias and torques and stuff like that, you can complicate things even more by having the pulley have like some resistance to acceleration. But currently all the Atwood questions you see are going to talk about like a massless, frictionless pulley and that sort of thing, so you don't have to worry about torques. So I'm going to show you three different ways that you can think about the same Atwood example. The first one is very systematic and aligns pretty closely with the techniques that I would have showed you last year in honors physics, but it's also kind of tedious. And then I'm going to show you a slightly quicker version, and then I'm going to show you in like the most quick version. And naturally, when you're taking like an AP exam, the quickest version that works for you, the quickest version that makes sense to you, is the one you want to go with. And so hopefully the super quick version will work for you. But if not, you can do one of the more careful ones instead. I've already written everything out, and so when I go to the next slide, you're going to see the whole thing. And I am going to try to like point at the parts that I want to talk about as I go. So let's look at the first version here. So you can see the diagram over on the right. I have this big pulley, mass of 5 on the left, mass of 3 on the right. I think I didn't actually use the numbers, so you can just refer to them as big M and little m, because I did everything algebraically anyway, just with the letters. So the first approach is with a really standard choice for the reference frame. I'm going to say that up is the positive direction and down is the negative direction. And to analyze this system, similar to what you would need to do in any Newton's third law problem, where there's multiple objects, you need to think about the forces felt by each object, analyze them individually, find some way to combine those statements, and eventually figure out the acceleration. The goal here is to get the acceleration of the system. So like obviously the heavy block is going to drop and the lighter block is going to rise up. So let me sketch a couple forces on here. That's the one thing that I apparently forgot to do ahead of time. I'll make my forces in green. So for the heavy block, I've got gravitational force going down. I don't want to call it Fg. I'm just going to write big M times G. That's the magnitude. And then this block is also connected to the string. And so there is a tension pulling upward. And I'm going to use the shortened notation and just call that tension big T. And then for the small block, I again have gravity going down, but this time it's little m times g. And it's also touching the string, and so it also has a tension T. Notice that I used the same name for both tensions. One way you can think about that is that the string, as long as it is an idealized massless string, the string is basically just a way of transmitting force between the two blocks. So like, I've got the force of the big block on the little, and I've got the force of the little block on the big, and the string is just the like medium for transmitting that force in a way. So those two forces have to have the same magnitude, and they both point up. That is true, and up is like the same direction, at least with the reference frame that I've set up. But those two forces, they do point, how do I put it? If I were to like unwrap the system, if I were to straighten it out, those forces then are pointing opposite of each other. I don't know if that's making any sense. The other way to think about it is just that anytime you have a massless string, the tension is the same everywhere in the string. Tension is a contracting force. So as long as the string is massless and the pulley is massless and frictionless, blah, 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 it's going to be the same tension on both ends, basically. So almost every problem you see all year that has a string in it, the tension will be the same on both ends. Only occasionally will that change. So I've written out forces for both of the objects. For the big block, mass times acceleration. I said A sub B, B for big. And there's two forces acting on that block. There's tension going up, there's its weight, big mg, going down. And then I did the same thing for the little block. Mass times acceleration, tension up, gravity down. The next thing I did was subtract these two equations from each other. So on the left-hand side, I have ma big minus ma small. On the right, I've got this, t minus mg, minus the other t minus mg. So obviously the t's are going to cancel out there. One way that you can think about that is what I was saying in the previous video, that internal forces will never have an impact on the acceleration of the system. The tension is an internal force because the system here is the blocks, or the blocks and the string, if you want to call it that. But regardless, the tension is a force that's between pieces of the system itself. And so it can't have an impact on the acceleration. And you can see it cancels out in the algebra. What I did next was just a little bit of rearranging. I gathered up the g's here. And then I made this new statement. Acceleration big equals negative acceleration small. And what I mean there is, suppose that the big block ends up accelerating downward at like 2 meters per second squared. That means that the little block must be accelerating upward at 2 meters per second squared. The only way that the magnitudes of their accelerations could differ would be if the string was like stretching out or something like that, but it's just an ideal string. It doesn't stretch, it doesn't contract. So the magnitudes of their accelerations have to be the same, but one of them is up and the other one's down, so their signs are opposite. So I took that statement and I replaced AS with negative AB. So you can see the sign here changed. And then a little more algebra gets me to this result for the acceleration. Notice that big M minus little m, that's going to be positive. And so this explicit minus sign here that I ended up with tells me that the acceleration for the big block is negative. It's accelerating downward. So that's what I would have guessed, and that's what I got by going through my algebra. Okay, approach number 2. This time, instead of up positive and down negative, I have a single unified positive direction, which I'm calling forward in my description here. Basically, if you know the direction of motion of a thing, it's often easiest if you choose the direction of motion, or the direction of the acceleration, I should say. It's often easiest if you choose the direction of the acceleration to be your positive direction. So the way I'm setting this up is that for the big block, positive is down, and for the little block, positive is up. Basically, whichever way they're going to go. And I even indicated that with this like funny curved axis that goes around this way. So setting up the algebra works the same as before. For the big block, I'm going to do MA equals the sum of the forces. Oh my goodness, I made a mistake, and I'm gonna go ahead and fix it in real time. So for the big block, the tension is negative because it points up, and it's the gravitational force that points down, mg. For the small block, it is the opposite. The tension is the forward force, and gravity is the backward force. Now this time, instead of subtracting the equations from each other, I'm going to add them, because the t's already have opposite signs. My goal is to get rid of t. So if I just add the equations together, on the left I'm going to have ma plus ma, and on the other side I'm going to have mg minus mg. Okay, that's correct now. On the left-hand side, I factor out the a. I don't need to do that like sign change on the accelerations this time, because both of their accelerations are in the forward direction anyway, so I can just use the same symbol a for both of them. The tensions cancel out. And that leaves me with big mg minus little mg. So that minus sign that I've got there is part of the same mistake I made before. But that line is now correct. The big M is positive, just like it was above. The little m is negative. And so if I solve that for A, I'm going to remove that minus sign again, because that was still an artifact of my previous error. I solve for the acceleration, and I get this expression. So the difference between this answer and the previous one is the minus sign that I just erased. If I flip back to the previous page, you can see the only difference in the answer is that explicit minus sign in front. The reason that I don't need the explicit minus sign in front this time is that I defined the direction of the acceleration to be positive. So it should come out positive, and that's what I've got now that I fixed my mistake. So this method is a little bit easier than the first one I showed you, because I don't have to have that extra statement with the two separate accelerations, where I like define one acceleration to be the opposite of the other. It's a little bit easier to keep track of. But there is yet an even easier way, which I'm going to show you now. And I've done the same stupid thing with the signs, so let me move some things around. now everything is great. The approach that you can take to solve an Atwood system even faster than that is to think about it this way. This is still mass times acceleration equals net force. But instead of analyzing the two different blocks or the two hangars as separate objects and then combining the two statements together with algebra, you can just treat the thing as one big system right from the start. So the mass that I want to include is the total mass of the system. And the force that I want to put here is the total amount of force along the axis of motion. And that still applies even if my axis is this funny curved thing. So the total mass here is big M plus little m. And the net forward force, or the total force along this axis, is going to be the force of gravity pulling down on the big block minus the force of gravity pulling down on the little block. I don't need to include the tension at all, because the tension doesn't affect the motion of the system. The tension's an internal force. It transmits force between the two blocks, but they're both part of the system. So the only forces that actually matter for the acceleration is the force of gravity on the two ends. So the big weight minus the little weight. Big weight minus little weight. Solve it for A. Get the same expression yet again, but way faster. So when you're doing the actual AP exam and you encounter Atwood machines, which you definitely will, this third approach is the way that I recommend, assuming that it makes enough sense to you that you can do it consistently without making errors. I recommend this way because it's simpler, so if it does make sense to you, you're much less likely to make errors than in the more complicated approach 2, and especially the most complicated approach 1. Approach 1 might make a lot of sense to you because it's all stuff that you've done many times before, but there's kind of a lot to keep track of. Whereas approach 2 removes some of that complication, but introduces this weird idea of the twisted axis. And then approach 3 is even simpler. So again, if approach 3, if you have any intuition for it, if it kind of feels like it makes sense, approach 3 is the way to go, because again, you're less likely to make a mistake because it's simple, and it's also way faster. And time is always an issue on AP exams. So any techniques that you can learn and master that are going to save you time, the better off you're going to be when you take the exam. Okay, so you'll see a lot of Atwood problems in the problem sets that we're going to do, as well as in the practice problems that I'll give you from old AP exams. And whenever you can, this third approach is the one that I think you should try to apply.